globular clusters in the Virgo cluster of galaxies. And this is work that's primarily, the hard work of Elisa Toloba, who was a postdoc here until recently. She's a junior faculty at the University of Pacific now, but also a collaboration with Eric Peng at Peking University, Alessia Longobardi, a postdoc working at PKU, Sung-Sun Lim, another postdoc there, Biao Li, recent graduate student. And I wanted to highlight the work of two groups of high school students, one set from this summer, some of whom are in the room right here, Teddy, Tiffany, Adara, Covid, and Jin, and then a bunch of high school students from the previous 3 years whose contributions you'll see in just a few minutes. So this particular survey depends on, it's really a combination of two different surveys. So there was a photometric survey carried out with the Canada-France Hawaii telescope and Mega Cam imager. This is a 1 degree by 1 degree imager that was pointed to the Virgo cluster as part of a large survey led by Laura Ferresi and Pat Cote. They covered 104 square degrees in the Virgo cluster, and strange as it may seem, this is the best digital imaging data set of the Virgo cluster. Most of what we know about galaxies, nearby galaxies, comes from the Virgo cluster, and most of that, for a long time, relied on photographic plate information and people's eyes to do the measuring and searching for different types of galaxies. So this is really bringing the Virgo cluster into the digital age with CCD photometry. So the NGVS is 104 square degrees covered in the UG, I, and Z bands, so UG, I, Z, with the central 2 degree by 2 degrees around M87, also covered in the R band, and most importantly in the near-infrared K filter. So that used not Megacam, but Wirecam on CFHT. So it's really this, mostly a 4-band survey of 100 square degrees, 104 square degrees, but the central 4 square degrees, 2 by 2 degree around M87, has these two extra filters in the R filter and the K filter. I'll show you some CMDs in a bit. But our contribution to this, the UC-HiPACC group's contribution to this, has really come using a different set of telescopes, which are the Keck telescopes in Hawaii that you see appearing here. This is a Laurie Hatch photo of the two Keck telescopes in a Mauna Kea sunset. And we used the Demo spectrograph that Sandy built and the Keck 2 telescope to survey specifically globular cluster candidates in the Virgo cluster that had been identified using the NGVS CCD photometry. So again, these are the main players. Elisa Toloba has led much of this work, and the high school students from this summer, Tiffany, Jane, Adara, Covid, and Teddy's work is also something I'll show. Okay, so we had 2 observing runs with the Keck telescope, and the totality of data we've collected so far corresponds to 2 nights, really 1.5 nights to survey satellites of dwarf elliptical galaxies in Virgo. This is, these are 3 half nights in 2012. And we had a half night this year. It was a 2.5 night run that got weathered out. All we were left with was a half night to study globular cluster satellites of ultra diffuse galaxies in Virgo. So here's some quick statistics from the 2 runs. It's a total of 2 nights. We used the 600 line grating on Keck and Demos, wavelength coverage from H beta through the calcium triplet. This would be considered the low end of medium resolution, so R of a couple thousand at the calcium triplet. We had a total of 12 multi-slit masks. Typical exposure time about 1.5 hours per mask. We had 21 DE targets, so many of these masks doubled up, and we were able to observe 2 or 3 or even 4 galaxies on 1 mask. So 21 DE targets and 3 ultra-diffuse galaxy targets, with over 300 globular cluster candidates targeted. This is going down to G of about 24, apparent G magnitude of about 24. Using a combination of the NGVS to select targets and some HST pointings at the centers of DEs to select globular cluster targets as well. We had a few hundred filler targets, main sequence turn-off stars in the Milky Way halo and the foreground of Virgo, but I won't say very much about them. So here's a color magnitude diagram, G minus I on the x-axis, apparent G magnitude on the y-axis. And the main feature you see here, this thing that looks like a hockey stick, is the Sagittarius stream. This is a group of stars at a common distance from us, and you're seeing a second concentration at brighter magnitudes, closer distances. This is the so-called Virgo overdensity that's thought to be a warp of the Milky Way disk. But what I'm going to focus on is this really hard to see plume of objects here. And you could barely see this plume in the Hess diagram, but most of these objects are globular clusters in Virgo. We targeted bright and faint things. You can imagine at the bright end, most of these objects end up being foreground Milky Way stars. This is the distribution of our Deimos masks in relation to M87. And just to give you a sense of scale, we've got roughly 5 degrees on each of the X and Y axes. So this is a small portion of the NGVS survey. And the gray data points are just an alpha to the -1 power law distribution. They don't represent real objects in Virgo. But we had these 9 Deimos masks. You can see the footprint of each Deimos mask here. We had, sorry. We had some overlapping masks, as you can see there and there, so that we could pick different position angles to target more satellites around some of these more better populated DE galaxies. Okay, so one of the things that I will just briefly mention, and I won't show any slides for it, is many of these DE galaxies end up having 3 or 4 satellites. That's all. Per galaxy, 3 or 4 satellites. The way we identify these satellites, globular cluster satellites, is to say we're looking for a coincidence in sky position and radial velocity. So if a globular cluster lands close to a dwarf elliptical galaxy, both in sky position and radial velocity, we call that a satellite. And we use some reasonable limits to define what a satellite is and what a non-satellite is. And there's actually a pretty clear separation between satellites and non-satellites. So we have a total of 80-some satellites of DE galaxies for 21 host galaxies. So it's average of 4 satellites per galaxy. And you really can't do very much with 4 objects per galaxy. So one of the things we are doing in the process of doing is stacking the sample and saying something about the average dark matter halo in DE galaxies. One other thing that we've done and published now is some of these DE galaxies have more than 10 satellites each. So they might have 12 satellites, 11 satellites. So we took 3 of those such galaxies with substantial number of satellites, and substantial means about 10 in this case. And we asked, are these systems of globular clusters rotating? And we did this because there have been 3 published claims based on similar sample sizes, 10 globular cluster satellites around a DE, been claims that rotation is seen in these globular cluster satellite systems. So we re-examined these 3 published data sets. We examined our own 3 galaxies. And what we found is in none of the 6 DE galaxies do we see significant evidence of rotation in the globular cluster system. And I emphasize the word significant. We did a bunch of simulations where we threw in non-rotating systems, selected the appropriate number of satellites, selected from an appropriate error distribution. And the error distribution really matters because if you, the better your velocity errors and the bigger your sample size, the more subtle a rotation signature you can detect. And the bottom line is none of our 6 galaxies, not our 3 and not the 3 published, so show any significant signs of rotation. So I'll just leave it at that and then move on to the next phase. So the other thing we found in our sample of satellites is we found a significant number of satellites that don't look like they belong to a dwarf elliptical host. That is either in sky position or in radial velocity or both. They have no nearby neighboring galaxy. Okay. So they don't seem like they are obvious satellites. So we label these things either M87 globular clusters at very large radius from M87, or perhaps more appropriate to call them orphans for the moment because we haven't identified their parents yet. So one of the nice things about these Orphan satellites, they're shown as this light blue cumulative radial distribution here. They look like, roughly like an alpha to the -1 power law in surface brightness space. And sort of reassuringly, the things that have star-like velocities, these green things, look like they have a uniform distribution across the face of Virgo, which is sort of reassuring. Okay, so the crazy thing is these Orphan globular cluster satellites, if you want to associate them with M87, is we're seeing them out to 100 effective radii, out of 100 times M87's effective radius. So I'll come back to this in just a few minutes, but some work that, that's in progress right now on the velocity distribution of these very remote globular clusters. Let me call them Orphans for now. These Orphan globular clusters in the remote parts of Virgo seem to have a bimodal distribution. I don't mean bimodal in color in the traditional way of globular cluster colors. They're certainly bimodal in color, but their velocity distribution suggests two populations. Suggests there's a population associated with M87 and a separate population that is offset in terms of mean velocity, offset and different in terms of velocity dispersion from M87. And that second population, the mean velocity of that second population is in better agreement with the galaxies in Virgo than M87 is with the velocity of the galaxies, the mean velocity of galaxies in Virgo. So we're calling the second population an intra-cluster globular cluster population versus an M87, remote M87 satellites. One of the tricky things in this business is the globular cluster population is really sparse out in these outer parts of Virgo, and you really worry about foreground Milky Way star contamination. One of the nice things about using the K-band is you start to see a separation between stars and globular clusters. The things that are marked in blue and red have globular cluster-like velocities. The things that are marked in yellow have Milky Way star-like velocities, and you see not a perfect separation, but a relatively good separation between these two populations. So one can select globular clusters in a pretty complete and reliable way using colors alone, and then study velocity distributions based on these populations. Okay. What separates this Keck-Demos sample from previous work in spectroscopic work in by the NGVS group in Virgo is this is using a slit spectrograph on a 10-meter telescope. In the past, they've used hectospec, which is a fiber spectrograph on a 6-meter telescope. And so we have a similar velocity distribution to this study by Hongxin Zhang, which is the black and blue points come from this MMT survey. Our Keck points are the triangles. You notice they're further out in radius than the Hongxin samples. We work further out in the cluster. But most importantly, they're quite a bit fainter. You can see an apparent magnitude now on the y-axis. They're quite a bit fainter than the typical MMT hectospec sample. And you know, it simply wouldn't be possible to get large numbers of these without the power of the Keck telescope. So this allows us to sample, to build up good sampling in the outer regions of the cluster. Now, having said this, the individual spectra of these globular clusters bring tears to my eyes, and not the kind of tears you're thinking about. They really are low signal to noise because these things are faint, especially if you're looking in the H-beta and magnesium B region. These things are really faint. An individual spectrum might look, really, really faint. So there's an example of an individual spectrum. Now you're wondering, how did we pull out a velocity? Well, if you get further to the red, if you get to H-alpha and you get to the calcium triplet, and with a tiny amount of smoothing of the spectrum, you can clearly detect H-alpha and the calcium triplet. Now, if you coadd these, if you shift these spectra based on the calcium triplet and the H-alpha line, if you shift 60 of these spectra, or 10 of these spectra, in this case it's 15 of these spectra shifted to rest frame and then coadd them, then you start to see in the coadded spectrum, you start to see the magnesium triplet at 5170 and the H-beta line at 4861. Thank you. So using these coadded spectra now, the students have taken different groups of globular clusters and compared their line strengths. And very roughly speaking, the H-beta line its line strength can be used as a proxy for age, the average age of the population, and the magnesium triplet here, the strength of that can be used as a proxy for metallicity. We're using modified Lick indices to do this. They're using this, and here, for example, is one such comparison. So the yellow point are the satellite globular clusters of DE galaxies, contrasted with these orphans over here. And because these globular cluster populations have blue and red peaks, bimodal distribution, we've compared blue globulars to blue globulars only. And what you see is a suggestion that the orphan globulars, as the M87 satellites and intracluster globulars, are more metal rich. That's the main thing that's changing along the x-axis. The grid lines are not perfectly orthogonal, of course, but it seems that the orphan satellites are more metal rich than the DE satellites, which could be indicating that the orphan satellites are the result of the disruption of galaxies that were, on average, larger than the surviving DEs in Virgo today. So they're much more metal rich than again, orphan GCs are much more metal rich than their globular cluster, than their DE globular cluster satellite counterparts. Surprisingly, though, the two populations have very similar color distributions. You can barely tell them apart. This is looking at the orphan globular clusters and the satellite globular clusters. These are two slightly different ways of. This is the blue and red populations, and I don't know if you can see this inflection here. There's a tiny red population and primarily a blue population, but whether you compare the full color distribution or only the blue on the left, the two distributions look very similar in color space. This is saying that, while globular cluster colors are related to metallicities, colors are quite a blunt tool to infer metallicity. Spectra are better, of course. Here's another comparison, now comparing these so-called intracluster globular clusters with the M87 globular clusters. This is, intracluster globular clusters in red over here with the M87 globular clusters in blue. We have a very small number of M87 globular clusters at the present time. We're trying to build up this sample. But if I take this at face value, it suggests that the M87 globular clusters may be more metal rich. Now, I'm not too concerned that this is below the grid. We shouldn't take the grid too seriously. And secondly, it's below the grid by less than 3 sigma. So we're trying to improve that, increase that sample size and see really what the intracluster versus M87 population, how they compare. Okay, so to summarize, I want to make 3 points. The globular cluster satellites of DE galaxies are definitely more metal poor than these orphan globular clusters we found in the Virgo cluster. And this suggests that these globular clusters have been orphaned from galaxies that were more massive and presumably more metal rich than the surviving satellites of DE galaxies in Virgo today. There's a hint that if we take the orphan globular clusters and divide them using velocity into 2 subsamples, the M87 satellites and the intracluster globular clusters, there's a hint that the M87 globulars are more metal rich than the intracluster globular clusters. We need bigger samples and therefore, more objects to co-add and better spectral signal to noise to really nail down that second point in the second bullet. And then, even though I didn't show you any plots from this, contrary to previous claims, we see no significant rotation in the globular cluster satellite systems of DE galaxies. In fact, we've written a paper trying to map out what kind of sample sizes and velocity errors it would take to nail down V over sigma in DE systems. It really depends on that ratio of V over sigma. The bigger sigma is, the harder it is to measure rotation. And that's where I'll stop. Thank you. Just preliminary stuff so far. One of the things we're trying to compare are the satellites of UDGs to satellites of more normal galaxies like dwarf ellipticals. Jury is still out, but we really got hammered by the weather. We had 2.5 nights to study this. We got half a night, so I'm hesitant to hang my hat on any result there yet. Yes, David.
Do the DEs have rotation?
The DEs are a real mystery in this sense. So the DE, you mean the main body of the DE, not the satellite system. So, they have odd kinematics. Let me explain. So first of all, it's done in integrated light, so you can't go out very far. You go out to 1.5 effective radii, whereas these satellites go out to 8, 10 effective radii. So we're talking about different radii for one thing. Some show rotation, some don't. But of the 6 we looked at, they in fact, there's a mix. A couple show rotation. In general, some show rotation, some don't. What is really intriguing about the DEs is if you put a long slit down along the major axis, about 30% of them, the 2 halves of your long slit, don't give you the same velocity gradient. So calling them rotation is a little dicey there because the 2 halves don't agree with each other within the errors, and we've now compared across different groups in the literature measuring the same galaxies with the same slit, and these kinematic anomalies in the outer parts of DEs exist, and we don't really know what they're about. One of the things we're trying to do is image them with KCWI and try to get full 2D kinematic mapping.
Any more questions? Well, if you try to sample if you stack the objects which you rejected as being Globular associated with the they're not necessarily orphans either, right? What are their characteristics in terms of age and
So you're talking about non-satellites of DEs?
Well, you find a candidate, you say, this one's close, etc. You say this one looks like a possible satellite.
Right.
The ones that are not.
That's right. That's exactly what I'm calling orphans. So the orphans are, of course, every Milky Way star shows up in this orphan space. And so our main task then becomes to separate the Milky Way stars from these non-satellites. That's called the non-GC satellites. So there's a significant number of objects, several tens of objects that we have in our sample that have globular cluster-like velocities. Part of the point is the Virgo cluster overlaps the Milky Way completely in velocity space. Of course, has a much wider range of velocities, but completely overlaps it. So we use color, and velocity information to separate Milky Way stars from these orphan globular clusters, and that's the analysis you saw.
Okay. Then I remember that M87 is not far from the center of the Virgo cluster. So you had a cluster-centric measurement. Can you distinguish that between the outer regions of M87?
Not in position space, but in velocity space, we are starting to see a separation. M87 is not at the mean velocity of the mean galaxies, and that we're starting to see in the satellites, in these orphans. We're starting to see. Some are and some are not. That's exactly the intracluster population versus M87 satellites I was talking about. That's exactly. Move on. Yeah. Okay. All right. Thank you.